Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be starting Unit 4. We're going to be doing Unit 4, Lesson 1 on Introduction to Linear Functions. Now this unit is all about linear functions, so of course today, even though much of what we're going to be doing is going to be review, it's extremely important for the rest of the unit. So make sure you're ready for that. I am going to be using my graphing calculator just a bit today in order to generate tables of values for some linear functions that I'm then going to go on to graph. So you may want to have your graphing calculator ready. As always, I'll be using the TI Inspire CX, so if you've got that one, you're good to go, and if you've got another one, hopefully you'll also be able to produce tables of values. Anyway, let's get right into it and discuss linear functions. One of the most important types of functions in math and science is known as a linear function. Now these functions are known as linear because their graphs consist of points that lie along a straight line. In other words, if I put a bunch of inputs in and I get a bunch of outputs out and I graph them as XY coordinate pairs, they should, in theory, lie on a straight line. So let's take a look at a linear function in exercise number 1. All right, the function f of x equals 2/3 times x plus 4 is a linear function. It can also be written as y equals 2/3 x plus 4. So just for a moment, I just want to mention this, right? Functions are sometimes shown with function notation like this, and sometimes they're just shown as y equals, okay? Either way, f of x and y, right, are really the same thing. They are the output of the function. So let's take a look at letter A. Find the value of f of 9. What point must lie on the graph of the function based on this calculation? All right, so even though I may fill out this table with the help of my graphing calculator, I'd like you to try to figure out what the value of f of 9 is by hand, and also what point must lie on the graph given your answer to letter A. Pause the video now. All right, well, this is just function notation, right? So f of 9 is going to be equal to 2/3 times 9 plus 4. Ooh. Never forget that when you multiply by a fraction, what you're really doing is dividing by the denominator and then multiplying the result by the numerator, which gives me 6 plus 4, and that's 10, right? Now, what that tells me is that the point 9, 10 must lie on this graph, right? And we always want to feel comfortable with that, right? The number that's sitting in here is the input. The number that comes out is the output. And then when they are graphed, it becomes input, comma, output, x, comma, y. Okay, so we know one point that lies on this graph, but we want to get a bunch of more points just so that we can verify that the points do lie on the line. So let's take a look at letter B. Fill in the table below for this function. Plot the points and connect with a straight line. All right, now, one thing that we could clearly do is that we could put every one of those x values into the formula and generate an output. There's no question about that. In fact, we'd already have it done for x equals 9. We'd only have to do it for the other 4. But I think this is a great time to bring out the graphing calculator and have it help us. So here we go. Coming out with the TI Inspire. I already have it on my graphing screen. We already have function notation there, so I'm going to be putting in 2/3, right, times x, all right, and then what was it? 2/3 x, I've already forgotten, plus 4. And I hit enter. All right, I can see that it all looks right. In fact, it's already graphing it as a straight line, but I want to get a table of values, so I'm going to go into my table, put a split screen table there. Now, a bunch of these answers are very, very messy because of that 2/3. But I can just kind of scroll through my table. I see when x is -3, my f of x is 2. And that means that the point -3, 2 must lie on my graph. Likewise, I see when x is 0, my output is 4, which means the graph 0, 4, or sorry, the point 0, 4 must lie on my graph. When I go down to x equals 3, I find out my output is 6, so 3, 6. When x is 6, my output is 8, so the point 6, 8 lies on the graph. And just to verify that calculation that I did before, when x is 9, my output is 10, so 9, 10 lies on my graph. Okay, let's graph this thing, right? So we're going to go over to -3, 2, 0, 4, 3, 6, 6, 8, and 9, 10. I really should have had my ruler out right now, but I didn't have the foresight to do that. So I'm going to freehand this. You should definitely, that was beautiful. You should definitely use a straight edge. Otherwise, you'll have what just happened to me happen to you. But there's my line, right? I should draw arrows at both ends of it unless for some reason they've restricted the domain on me and said, hey, just go from this x value to this x value. This table of values doesn't imply I should only go from -3 to 9. It's just kind of giving me a basis to actually draw the graph. All right, so not the most beautiful straight line, but hopefully, plotting those points have kind of given you faith that they do lie in a straight line, even though my drawing is terrible. All right, let's take a look at letter C. In the table, what is the average rate of change between any two consecutive x values? Circle this value in the equation and illustrate it on the graph. All right, this is kind of cool, and I really want you to be able to look at average rate of change by looking at a table, right? Remember, average rate of change is the change in the function's value divided by the change in the value of x. That little triangle standing for the Greek letter delta means change in. And of course, that's the same as the change in the y divided by the change in x. Now, one thing I just want to illustrate is that the change in x in this table I've kept to be consistent, and it's always +3, right? I always have a change in x of +3, right? Add 3, add 3, add 3, add 3. And I did that because that fraction has a denominator of 3. So my change in x is 3. On the other hand, when I look at my change in y, right, I'm adding 2 each time. So my change in y, please excuse the fact that I'm drawing through the coordinate points, but each time my y increases by 2. So my change in y is 2. So my average rate of change in every single one of these intervals is 2/3. And we see that in the formula itself, right? There it is. There is the average rate of change. And we can see it on the graph because if I grab any 2 points, for every 3 units I move to the right, I move 2 units up. And then I move 3 units to the right, and I move 2 units up. And 3 units to the right, and I move 2 units up. And that is really what makes a linear function, is that the rate of change is no longer really an average rate of change, but it is always, for every 3 units to the right, I go 2 units up. For every 3 units to the right, I go 2 units up. You could think of it as for every 1 unit to the right, I go 2/3 unit up, but that would be a little bit confusing. All right. Now the other piece is letter D. What is the function's y-intercept? Circle it on the equation. All right. Well, again, let's just talk about this. This is very, very simple, right? We can look right here, right? There's our y-intercept. We can even see it in the formula, right? The y-intercept always occurs where the input is 0. So the y-intercept is y equals 4. And that shows up right here in the equation, right? There is our y-intercept. And I'm hoping that a lot of this sounds familiar from your last math class, right? In your last math class, you should have learned that the slope, or the rate of change of the line, will always be the coefficient of x, and the y-intercept will always be the number that is added on to that x term. So in fact, let's kind of summarize this. I think that was the last of that problem, you bet. Let me move my calculator a little bit out of the way. Let's talk about the equation of a line, right? You should be familiar with the equation of the line from your last math course, and we're going to now just use that to define what a linear function is. In other words, a linear function is any function that looks like a number times x plus another number. Okay, and that plus another number, that other number could be negative if the y-intercept is negative. Oftentimes we just write this as y equals mx plus b, right? Where the m is the slope, also known as the rate of change, right? We sometimes call it the rise over the run being the horizontal movement and the rise being the vertical movement. And the number that's added on is the y-intercept. It's the value of the function when x is 0, and that should make all the sense in the world, because if I plug x equals 0 into this formula or this formula, and I multiply it by m, I get 0, and when I add it to b, I get b. So that is just literally the definition of what the y-intercept is. When I put x equals 0 in, the m times x goes away, and all I have left is the value of b, right? The thing that's a little bit trickier is the idea that the coefficient on x, when this is written in this form, represents the slope of the line. Again, the idea, very simple, is that if I go to any 2 points on the line, if I grab any 2 points on the line and I measure how much the x value has changed and I measure how much the y value has changed, if I divide that change in y, right, by that change in x, that will give me the number that's multiplying x, right? That will give me that slope or rate of change. How fast is y changing compared to a change in x? In our previous example, we saw that when x changed by 3 units, when x increased by 3, y increased by 2. So let's get a little bit more work with equations of lines. Let's take a look at exercise number 2. For the linear function y equals 5x plus 2, choose two x values and show that the average rate of change between the two is equal to the slope of the line. All right, I love this exercise. I'd like you to choose two x values. Don't choose them as consecutive integers, okay? Don't choose 1 and 2 or 3 and 4. Choose a couple x values that are separated by more than 1 unit. Calculate the y values using the function's formula, and then find the average rate of change between the two. If you've done everything correctly, that average rate of change should be the slope of this line. Pause the video now and choose a couple random values of x and calculate their average rate of change between the two. All right, I'm just going to go random. Again, I don't know, obviously, what you chose. So I'm going to choose x equals 1 and x equals 4. Okay? So when x is equal to 1, I can just do 5 times 1 plus 2, which is going to be 5 plus 2, which is 7. And keep in mind what that means is, right, I got the point 1 comma 7 on this graph. If I put 4 in there, I'm going to do 5 times 4 plus 2, which is 20 plus 2, which is 22. Again, right, what that tells me is that the point 4 comma 22 lies on the graph. And now if I do the change in y divided by the change in x, right, I'll do 22 minus 7, right, divided by 4 minus 1. Keep in mind, there's a nice interpretation of this, right? That means that between those two x values, y increased by 15 units while x increased by 3. And then if I do 15 divided by 3, I get 5, right? And there's that 5 right there. Okay, and I didn't choose any two magical x values. You could have chosen any ones whatsoever. If I'd chosen negative 167 and positive 322, and I had done exactly the same calculations, ultimately they would have all come down and divided out to give me an average rate of change of 5. Because the slope of a line, the rate of change of a line, is constant. And that's what makes it a line. Lines always travel forever, right? Forever and ever in the same direction, all right? The direction given by the slope. Let's keep going. All right. It is important to be able to graph a linear function by setting up a table of values on your calculator and plotting points, okay? It's beautiful, right? Back in my day, you had to do all of these things by hand. But the graphing calculator, the beauty of it is that it can produce these tables of values for us and allow us to quickly, easily, and accurately graph just about anything, not just lines. We'll talk about how to graph lines without using a calculator in the next exercise, but here I want to set up yet another table of values. Let's take a look at exercise 3. For the linear function y equals negative 1/2 times x plus 7, answer the following. Letter A, graph the line on the grid provided by creating a table of values. Show your table below. All right, again, I like to make sure that when we're doing something that involves calculators and calculator use, we make sure that we're kind of working through it together. So let's yet again set up a table of values together and then write down that table. I'm going to just create a brand new document for myself. That's not what I want. What do I want? I want doc, enter. I want a new document. I don't want you to save the old document, and I want a graph. There it is. Whew. All right, so what do I have? I have -1/2 times x plus 7. Enter. All right, I already kind of see a little graph of my line, but I'm going to kind of ignore that right now. All I want is my table, so I hit menu and I go to option 7. I'm going to put in a split screen table. And it starts at x equals 1 always, but what I do is I kind of move backwards to see how much I can fit, right? So, I can actually go all the way back to -6 because my grid goes up to 10. I can go back to -6. And so I'm going to create a table of values. I'm only going to include nice values. Quite frankly, I really only need a couple of them. I'll move my table eventually, but I've got x and y. So when x was -6, y was equal to 10. I don't think I'm going to include that one at -5 because it's got a little decimal in it. I could, but I think I'll now go with -4 and 9. Right, so now we'll go down to -2 and 8, 0, and 7. There's our Y-intercept, right, when our input is 0. 2 and 6, 4 and 5, 6 and 4. I probably didn't need to go to -6 given that my graph paper doesn't extend that far, but yeah, it's okay. 8 and 3, and I think I'm going to cut it off there. Okay, so I went a little bit further to the left in the table I needed to, given that -6 isn't on my graph paper, but that's fine. I'll start with the point -4, 9, right? So when I plot that, it's going to be right here. Then -2, 8, 0, 7, 2, 6, 4, 5, 6, 4, 8, 3, and I bet you could tell that 10 would be at 2. Again, make sure you're doing this with a straight edge. I'm going to just freehand it, which again doesn't look that great, but gets the job done. All right, there's my line. All right, now, letter B. What is the slope of this line? Illustrate on the graph. So what's the value of the slope? Slope is a number. It's an average rate of change. We already talked about where to find it in the equation. So pause the video now, write down what the slope of the line is, and see if you can illustrate it on the graph. All right, so, the slope will always be the coefficient of x when it's written in this form. So the slope is -1/2. Now, I'm going to like to think about that as -1/2, because remember, right, I want to think about the slope as the change in y over the change in x. So I can really think of this as, for every 2 units that x increases, y decreases by 1 unit. And I can really see that on the graph. If I grab any point and I move 2 units to the right, I have to go down 1 unit. Then move 2 units to the right, go down 1 unit. It's hard to write the 2 in any good way. There we go. Right? So I can see it, literally. For every 2 units of increase in x, I get 1 unit of decrease in y, so the ratio -1 to 2 is the same as the number -1/2. Letter C, this should be pretty obvious. Is this function increasing or decreasing? Why does it behave this way? Okay, write down what you think. Is it increasing or decreasing, number 1? And number 2, why is it either the increasing or the decreasing? Pause the video now. Well, remember, increasing and decreasing on functions, we talked about this in the last unit. I always want to read a function by looking at it from left to right. So if I was moving along this function from left to right, then I would be going downhill, right? My y values would be decreasing. This is a decreasing function. And there's one simple reason why it's decreasing. The slope is negative, right? The reason that this function decreases is because the slope is negative. In fact, anytime a rate of change is negative, what that tells you is that the function is decreasing over whatever interval you calculated the average rate of change on. Now, the cool thing about lines is that they're always decreasing, or they're always increasing, because they have only one slope. If the slope of the line is positive, the line will increase as you move from left to right. And if the slope of the line is negative, the line will decrease as you move from left to right. It's really that simple. All right. And it's amazingly important that you have that piece of the puzzle when it comes to lines and linear functions. Hey, I finally included a ruler. Now I probably won't be able to work it very well. All right, graphing lines by hand. It is helpful to be able to graph lines using their slopes and their y-intercepts without having to create tables of values. Now, don't get me wrong. There's nothing really wrong with creating tables of values, but there are situations where you'll have to graph lines relatively quickly, all right? And you'll want to be able to do them without having to put every one of them into your calculator, generate those XY tables, and graph them, okay? So let's review how we graph a line without having to set up a table of values. Exercise number 4. For each of the equations given below, write the equation in the form y equals mx plus b, if needed, identify the slope and the y-intercept, and then graph and label the line on the grid. All right, so in other words, like it says, write it in the form of y equals a number times x plus b. Now, in letter A, we're already written that way. Y equals 2 times x minus 3. I'm going to write that a little bit bigger just so that you can certainly see it. All right. And what's great about this is immediately we know that the slope is equal to 2. Now, since that's a whole number, I'm going to actually write it as 2 over 1, or the ratio of 2 to 1. The reason I'm going to do that is that then tells me, right, for every 1 unit that x increases, y will increase by 2 units. Now that's awesome, but I have to have a starting point. If I don't have a starting point, then it's pretty hard to use the direction or the movement of the line to draw the rest of the line. Well, I do have a starting point because the y-intercept, right, the y-intercept is equal to -3. That's very important, right? So I go down here to -3, and then how do I graph the rest of the line? Well, I go to the right one and I go up 2, and then I go to the right one and I go up 2. So right one up 2, right one up 2, right one up 2, etc. And this will give me a lot of other points on the line. I could also reverse and go to the left one and down 2 if I wanted to produce a few more points. And now let me see how bad I am at using the electronic ruler. It's been a little while. Now I'm kind of regretting that I didn't just stick with it by hand. Yeah, there we are. All right, almost there. Oh yeah, yeah. This is looking good. Nope, still bad, still bad. Oh boy. Well, I'm not sure that got any better than before. That's okay. We should always make sure when we graph more than one line on a graph grid that we label it with its equation. When it says label the line on the grid, what that's getting at is make sure that you put the equation of the line right beside it. Let's do another one. Letter B, y equals -x plus 6. Again, I'm going to rewrite this a little bit bigger, and I'm going to write it as -1 times x plus 6. Give myself a little more room there, okay? The slope, right, is -1. That's a little tricky. Please don't ever tell me the slope includes the x. right? You never want to say the slope is negative x. That doesn't make any sense. A slope is a number. It doesn't include a variable, all right? So the slope in this case, I can say is negative 1 over 1, and the y-intercept is positive 6. I will always write my slope when I'm graphing lines by hand as a fraction so that I can think about it as directions, right? Go to the right one, go down one. Go to the right one, go down one. From where? From a y-intercept of 6. So I'm going to come up here to a y-intercept of 6. I'm going to go to the right one and down one, right one and down one, etc. Right? Very quickly I developed this pattern. I think I'm going to just forego the electronic ruler in the interest of not taking all day to graph these lines, and given that's pretty good anyway, y equals negative x plus 6. All right, what I'd like you to do now is take a moment. I think the last two are actually probably a little bit more straightforward, and graph both of those lines and label them with their equations on this grid. All right, well, let's do it. Letter C is already written about as well as we can get it. Let me extend the page a little bit, right? Here, the slope is 2/5, again, telling me that for every 5 units I move to the right, I will go 2 units up, and the y-intercept is 3. So let's do it. We've got 1, 2, 3. Here's my y-intercept. I'm going to go to the right 5 units and up 2, right 5 and up 2. I can reverse that and go down 2 and to the left 5, and down 2 and to the left 5. And that's going to be my line there. That's going to be y equals 2/5 x plus 3. And finally, for letter D, the slope is going to be negative 3 divided by 2. The y-intercept is going to be negative 7, again telling me that for every 2 units I go to the right, I'm going to go 3 units down. So if I'm out here at b equals negative 7, I'm going to go 2 units to the right and 3 units down. And I'm going to run out of graph paper really quick, right? I can reverse that, go 2 units to the left and up 3. All right, there we go. Ooh, right through my other label. Y equals negative 3/2 x minus 7. You know, one thing I do want to mention before we kind of wrap this up is I very casually was like, oh, you know, you go 2 to the right and 3 up, and then you can just reverse the pattern. By the way, one of the reasons that you can reverse the pattern, let me move my b equals negative 7 out of there, is because we can look at the fraction negative 3/2 in 2 distinctly different ways. We can look at it as negative 3 divided by 2, but because a negative divided by a positive is equal to a negative, right, or a positive divided by a negative is equal to a negative, we can also look at negative 3/2 as being 3 divided by negative 2, right? And that's telling me left 2, up 3. So when you have a negative slope, you can attach that negative to the numerator or the denominator. You just can't attach it to both, because then you'd have a negative divided by a negative, and that would be a positive. Okay, so we're going to get a lot of practice graphing lines by hand. You've already done that quite a bit in previous courses, but you know, we want to make sure that you are very fluent with it before you leave this course. So today, right, we reviewed some very basics about linear functions that hopefully you've seen before, right? Linear functions are functions that when you plot input-output pairs all fall along a straight line, and importantly, they fall along that straight line because their average rate of change is always the same. It doesn't matter what interval you calculate it over, it will always be the same, and therefore we give it a special name. We call it the slope of the line. And we can see the slope of the line in its equation as the coefficient that multiplies x. We can then go on and graph equations of lines because we can also find a starting point at their y-intercept, which you can also see in the equation of a line. All right, way more work on this in the next lesson. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.